Hello, everybody. This is Mr. Beck, and today I would like to talk to you about the last topic in terms of graphing rational functions. So it's really going to be a combination of all the stuff from 4.2 through 4.4, because 4.4 also deals with rational inequalities. So we're going to be looking at not just the equations and graphing them, we're going to be looking at them as inequalities as well. So beginning of today's notes are really going to be our 4.2 review. On our 4.2 review, basically, what are all of our skills that go into what we're doing here? Skills that are going into graphing are how do we come up with vertical asymptotes? Vertical asymptotes occur when you have a number over 0. Now, a hole occurs when you have 0 over 0. There are some exceptions to that, but primarily we are going to focus on what happens when we have 0 over 0. It's going to be a hole. Then we have, how do we find that out? We set our denominator equal to 0 and solve. Then when it comes to horizontal asymptotes, we have two different types of horizontal asymptotes we're going to be looking at. The first that stems from a proper fraction. The proper fraction is when the numerator has a smaller degree than the denominator. So the numerator has a smaller degree than the denominator. So y equals 0 ends up being that horizontal asymptote. And then if we have an improper fraction with the same degree in the numerator and denominator, so numerator degree equals the denominator degree, and maybe I should put degrees here just to be on the safe side. So if that's the case, then what we do is we look at what's called the ratio of the leading coefficients. So if this is a times like x squared over b times x squared plus whatever, y equals a over b is going to be our horizontal asymptote. Then we have some other asymptotes. What happens in the third case if the numerator has a greater degree than the denominator? Officially, this is an improper fraction as well, so numerator greater than the denominator. Now, based off of how many degrees that we have, if it's 1 degree above, we have a linear asymptote. If we have 2 degrees above, it's a quadratic asymptote. 3 degrees is a cubic asymptote, et cetera, et cetera. How far are we going to go here in this course? We're only going to go 1 degree above. And that's what's going to create our oblique, aka our linear asymptote. Now, those are all the different skills that we practiced in 4.2, and now we're going to apply in 4.3 and 4.4. So to graph rational function, always look for asymptotes, and tied into the asymptotes is the domain there, followed by intercepts. We're really not going to focus as much on range right here, especially during our COVID situation. Intercepts, we set our numerator equal to 0, solve, and then plug in 0 to find our y-intercept. And the last bit, which is going to be very, very helpful, is determining where our function is positive or negative. We did this with polynomials, quadratics, and those inequalities. We're going to do those with rationals as well and turn them into inequalities. So without further ado, let's go on to our first problem. So our first problem, what I did was I factored. I factored my denominator because the factor x minus 3 tells me x equals 3 is a vertical asymptote. So x equals 3 is that vertical asymptote. Followed by x plus 2. That factor x tells us that x equals -2 is a vertical asymptote. Now, from this original form, we see that the degrees of these are the same. Because the degrees of those are the same, what that causes us to do is look at the ratio of the coefficients. Both those coefficients are 1, so y equals 1 is our horizontal asymptote, which I'm graphing right here. Next characteristic we look at are what happens when we plug in 0, meaning what is our y-intercept. So when we plug in 0, we will get 0. So our y-intercept magically becomes our x-intercept as well. So now we're going to test points. We're going to, what I do on a number line is I establish, let me actually color code it. I plot my zeros on the number line. And then I also plot, let me change it to the right color. I plot my 2 vertical asymptotes, and I plot those as open dots because we know the domain does not exist there. And then what I do is I test values in between. So for instance, what happens if I plug in, say, a 1? If I plug in a 1, I will get 1 squared, which is 1, over 1 minus 3, and that is I really should look at that as positive, over 1 minus 3 is negative, and 1 plus 2 is positive. A combination of 3, or like 1 positive and 2 negatives together, give us negative overall. Now I can do the same thing if I plug in a 4, I get positive, positive, positive. If I plug in, say, a -1, I will get a positive over a negative times a positive. And if I plug in -4, I get a positive over a negative times negative, which results in positive. But really, I'm plugging in numbers just like I did in my last two videos when I dealt with inequalities. I'm doing the same thing here as well. Now, what we're going to do with that information is, let's start off with that first. That is a positive region. So this part of the graph should be following the asymptotes in that positive region where all the y values are positive. Now, I do want to make a quick note, something that I always look at. There are no x-intercepts here, so the graph should not exist down here crossing the x-axis. The next region is negative, so I follow the asymptote, go up to the 0, and then the region following is negative, so from the 0 down to the asymptote. Now, does it surprise us that we go from a negative to a negative? And I'm going to say no, because one of the key ideas that I want you to focus on here is this exponent of 2 means I have a multiplicity of 2. That multiplicity being 2 even means I'm not going to change signs. If I look at the factor x plus 2, that has a multiplicity of 1, and because it's a multiplicity of 1, it should be changing signs there. So we're going to be using multiplicity just like we did when we had polynomials. We're going to be using multiplicity with the zeros and with our undefined values at the same time to determine if we change signs. So multiplicity of x minus 3 is 1. Since that multiplicity is 1, we should have changed signs, which in fact we did. And then that last region that we're going to graph is the positive region, which is up here. For part B, if you notice, one of the first things I did was I factored. By factoring it, this puts it into a form that is very beneficial for me to see. Why is it beneficial? Well, all the different forms that we write these in tell us different pieces of information, such as if I wrote this as x squared minus 4x plus 4, suddenly this tells me lots of pieces of information. Same degree, the leading coefficient is 3 over 1, hence y equals 3 is my horizontal asymptote. What happens if I plug in 0? If I plug in 0, I will get 0 over 4, which is 0. And now, by factoring the numerator, and then we turn this back here, by factoring the numerator, so in this form, that tells me really both x-intercepts at the same time. The denominator is already factored, which is nice. That denominator factored, let me change colors. That denominator factored tells us our vertical asymptote of x equals 2. And let me match up the colors here, y equals 3. So let's fill in the rest of the bits of information. So what I'm looking at here is, and I tend to start on the positive side. So I start on the positive side because typically those values end up being all positive anyway. And if we check, we get a positive times a positive or positive times a positive. Everybody, what I'm doing is I'm plugging into those factors. Positive, 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 positive. All positive means that we're going to yield a positive result. But now I'm going to try to be more efficient, where let's take a look and say, what is the multiplicity of that exponent? The multiplicity of that exponent tells me that the sign is not going to change there. Let's take a look in the denominator, the numerator. Both of these factors have a multiplicity of 1, which is why we change signs here and change signs here. So I'm expecting a sign change in both places. So with that in mind, then we are going to put everything together. So our positive region that I started off with gives us this side. This positive region will give us this. And we're going to cross the horizontal asymptote, which surprises a lot of people. We'll deal with that in a moment. Yes, we can cross horizontal asymptotes. One of the big aspects of that is because the horizontal asymptote, and I have it written up here, is what happens away from the origin. So we're going to find infinite limits when we do that. What happens is x goes to positive and negative infinity. That's what gives us a horizontal asymptote. So going back to this, then I pass through the 0 because the multiplicity of 1, pass through the 0 because the multiplicity of 1, and then I approach the horizontal asymptote again. Now, some strange things can occur when we get these horizontal asymptotes. I mentioned that we're crossing the horizontal asymptote here. I have, in fact, seen some graphs where it crosses the horizontal asymptote and then approaches like so. This graph doesn't do that, but I've seen that. So how do you know where it's going to cross the horizontal asymptote? It's going to cross the horizontal asymptote when the function that I'm working with, which is what I have here, equals the horizontal asymptote. So I really just set those equations equal to each other, basically solving the system of equations. And in solving that system of equations, then I cross multiply and then solve for x. So x equals 2/3. And if you notice, I have that point right up there. X equals 2/3 is where those two functions cross each other. Moving on to the next one. With the next one, once again, I factored. By factoring it, it allows me to see my two x-intercepts really, really well, 3, 0 and negative 2, 0. If I plug in 0, and this is where I'm plugging it back into the original form, I can see what my y-intercept is. My y-intercept is 0, 6. By putting it in the factored form, I get my denominator equaling 0. So the fact that my denominator equals 0 gives me that vertical asymptote. And now, since the numerator is 1 degree above the denominator, which we could see right there, that means that we're going to have an oblique asymptote. Now, to find that oblique asymptote, we're going to have to divide. So I will show you both long division and synthetic division. So when it comes to our synthetic division, which is what I showed you, the x minus 1 in the denominator means that there's a 1 that's going to go in this box. Synthetic division is really just a process. So we're going to have to interpret our results. Bring the 1 down, multiply by 1, add, multiply by 1, add, and I get that result. Now, what that result tells me is that this expression is equivalent to this expression, where I have x plus 0 plus negative 6 over x minus 1. So the x plus 0 is where I get my oblique asymptote. So my oblique asymptote. Now, like before, I did a number line test where I'm testing between 0, undefined, 0. So I have 4 different regions. And you could plug in the values yourself, or you could trust me that I go from negative to positive to negative to positive, hence negative through the 0 to the positive, the asymptote. Then negative from the asymptote to the 0 to the positive. On to our next one. So on our next one, this case, I did synthetic division again, and by doing synthetic division, I will turn this overall expression into x plus 5 plus 6 over x minus 2. Factored the numerator, just like I did with the other problems. So all the different forms give us different pieces of information. So first things first, by writing it into its proper form, this tells me x plus 5 is my oblique asymptote. Now, in any of the forms I'm working with, I should see this x minus 2 in the denominator, which gives me the vertical asymptote. And now by factoring, so in this form, this factoring gives me my two x-intercepts of negative 4, 0 and 1, 0. If I plug in 0 to any of these, if I plug in 0, I will get the y value of 2. Doesn't matter which one of the forms I plug it into, I'll get the y value. So I have my zeros, I have my undefined, and this one honestly is pretty easy to see that we're approaching the asymptote, going from negative to positive to negative, and then to positive. Now, how did I know it does not do this? 2 reasons. There is no 0, and the multiplicity of my asymptote is 1. Moving right along, this problem right here. So like before, in this case, I factored first, and by factoring first, I get it into that form. So 0 is one of my zeros and has a multiplicity of 2, which is why we can actually see that bounce occur right now. Negative 1 has a multiplicity of 1, which is why it goes through. X equals negative 2 and x equals 2 both have multiplicities of 1, which is why you could see on the graph that we're changing signs there. I know I'm kind of like lumping a lot of this together, but I want you to know the logic that's going on in my mind as I see all of these individual problems. So now, how do we know what our oblique asymptote is? Our oblique asymptote, this time we have to determine by, in this case, we can't do synthetic division because the denominator is a degree of 2. So we have to do some long division. Our first step in the long division process is how many times does x squared go into x cubed? That is x times. We subtract out x times x squared minus 4. Bring this down and then go through again. How many times does x squared go into x squared? Once. So then subtract, and I get 4x plus 5. This is now proper because the numerator has a smaller degree than the denominator. So this x plus 1 plus it's something else tells me that x plus 1 is going to be my oblique asymptote. Do our number line test. We go negative x plus 2 in the denominator has a multiplicity of 1, so we change signs. X plus 1 has a multiplicity of 1, so we change signs. X has a multiplicity of 2, so we don't change signs. And then at x minus 2, we have the multiplicity of 1, so we change signs. And we could sketch all negative, positive to negative to negative to positive. Now, part B is kind of interesting because some cool things happen. Specifically, when we do our factoring, so first I factored out the 2, and then I factored that quadratic. In the denominator, I factored by grouping. Factor an x squared out of the first 2 terms, factor -4 out of the second 2 terms. And now, as you can see here, I factored the x plus 1 out of both terms, and that's how I get x squared minus 4, giving me my overall factorization. What's going on here, or what's occurring, is we end up with factors that are the same in the numerator and denominator, aka if I plug in -1 to the numerator, I get 0. If I plug in -1 to the denominator, I get 0. So those are going to cancel each other out, creating a hole. So a hole occurs at x equals -1. This x minus 2 will cancel out with this x minus 2, so it creates a hole at x equals 2. Now, how do we find the location of the holes? This is where we use our limit process. So we will take the limit as x approaches both -1 and 2, and we will plug it into the reduced equation. By plugging into the reduced equation, we're going to get a number value. That number value indicates the y value where the hole occurs, which both of those are going to happen. Now, we still look at all the other characteristics that we have, but we could use the reduced equation to do that. So our denominator is x plus 2, which means that our vertical asymptote is x equals -2, and we can plot our points. Honestly, this is now just a straight dilation by 2 and translation left 2 units. Then we go backwards. So we're going to take the characteristics of the graph, and we're going to use the characteristics of the graph to create the equation. For instance, we know that -4, 0 is an x-intercept. Because -4, 0 is an x-intercept, that gives us the factor x plus 4 in the numerator right here. So I also have 1, 0. So 1, 0 gives me x minus 1 in the numerator. Now, why is it squared? Because we don't change signs. So x minus 1 squared. The third one, x equals -1 is a vertical asymptote. That vertical asymptote we see, whoa, bad drawing. Vertical asymptote we will see right here. That gives us the factor x plus 1 in the denominator. And if x plus 1 is in the denominator, notice how we change signs. By changing signs, then we're going to have an odd multiplicity. Now, on the last one, though, if you notice that we don't change signs at the vertical asymptote of x equals 2, which is why I made x minus 2 squared in the denominator. And now, what haven't we worked with? We haven't worked with our horizontal asymptote of y equals 2. What that tells me is our leading coefficient, which we officially don't know, should be 2. Now, how do we actually find that out? This is where I'm going to use my y-intercept as 0, 2. And I will say 2 equals a times 0 plus 4 times 0 minus 1 squared over 0 plus 1 times 0 minus 2 squared. So if you see 2 will equal a times 1, or just a equals 2. Over here, now for the record, I like this problem, but this problem could be a bit of a problem if it wasn't as simple as what I made it. So retrospect, I probably should have given a different one, but I wanted to see different aspects. So the different aspects of what's going on is I have to first use my oblique asymptote or my linear asymptote of y equals x minus 4. So y equals x minus 4, but now I have vertical asymptotes, and this is where away from that oblique asymptote or that linear asymptote, I'm going to use the vertical asymptotes to come up with the factors that are in my denominator. Now, x plus 3 has a degree of 1 because we change signs. X has a degree of 2 because we are not changing signs up there. Moving right along. This case, I really need to solve for A. And to solve for A, what I did was I found a point that was on the graph. Let me change colors so you can see a little bit more clearly what I'm doing. -1 comma -4 is on the graph, so I plug in -4 for y, plug in -1 for x, and solve for a. In this case, a equals 2 also. This is a simple case. It could have been a lot more complex, but it's not. Now, the last thing I want to do is I want to use the graph to determine where r of x is positive. We kind of are working backwards from what we did before. So where's r of x positive? So since this is positive up until -4, then negative up until -1, positive, and that's positive over here too, and then it's positive over here as well. So where's r of x greater than 0? In order to solve for r of x greater than 0, we need to locate all of our positives. But don't forget, it's greater than 0, which is why we are not including that point or that point. And last but not least is algebraically doing this. So algebraically doing this, it's really the same thing as what we did on the graphical level. We are just putting it in algebraically. So we already have this in its factored form. We're getting it to its factored form. So we put our 0 because of the factors in the numerator, put our undefined because of the factors in the denominator, test our signs, positive, negative, positive, positive. You know, if you don't trust me, plug in numbers, that's what's going on. And now I want to know where this expression is less than or equal to 0. So that's the negative values. So those match up, but we have a special case of x equaling 2 as well. Now this is where most students will miss points, and I really, really don't want you to do this. And I kind of pointed out in all my classes, pay attention to these part of the notes. What we need to do is like we had in part A. Part A was compared to 0. This is not compared to 0. So what do we have to do? We have to subtract 1, so it's now compared to 0. And then combine into one fraction. So to do that, I have a common denominator, join them together, and I get this overall expression. Once I get this overall expression, then I could test for positive and negative, and I get the answer from 4 to infinity. Where students make mistakes are they cross multiply right away, and you're not allowed to do that. Sometimes you will get the right answer, sometimes you won't. You really want to test it to say, hey, I got the right answer, but I really didn't know what I was doing. You must combine into one fraction, and I will be grading that way. So if you're not listening to this because you're not watching it, you are going to lose points because I am going to expect that you could put this all together into one fraction. And that's what I did for part C here. Hopefully the graph will shift soon. Part C, subtracted so that I'm now comparing to 0. Found the common denominator, so some algebra 2 skills kick in. Combine my numerators together, and then use the numerator to get my 0, use my denominators to get my undefined, and use number line tests. Where is it positive, where is it negative? Since I want to know all the positive values, that's why I have the solution here. For number 7, this looks crazy. This looks like a throwback to 2.1, which it sort of is. But what we're doing is we're saying what's underneath the even root must be greater than or equal to 0. Basically, we're solving this just like we did up above. The 0, the undefined, plus, minus, plus, and I want all the positive values, but also equal to 0. And that's one of the big reasons, everybody, I have an open dot at -3 and a closed dot at 6. The open dot represents the vertical asymptote. The closed dot represents an actual 0. On problem AE8, which on this problem, this is more of a polynomial one. So I substituted this in for R, and then this in for C. And in doing so, I now have a polynomial. Do some factoring. This is a trinomial. This is kind of like some lead-in practice for our next section, hint, hint, hint. So then I know that my only 2 real zeros come from x squared minus 1, so -1, and then do my number line test to get my answer. So I wish you all the best of luck, and as you ponder your notes, and have a great day.